So in today's lecture, we're going to talk about potential energy concepts and how we can use that to measure the direction of water flow in soil. Last week we talked about the water retention function, and essentially that describes how soils hold on to water when the soil is unsaturated. So when there's an air-water-soil interface, then water likes to stick to soil, and depending upon the pore size, water will be drawn into that soil, into those smaller pores with various degrees of energy. And that energy really is a matrix potential. It's a potential for the soil to hold on to water. But we're going to look at a whole bunch of other different potentials as well, which all contribute to the directions and magnitudes of water flow in soil. So some of those are pressure potentials, osmotic potentials, elevation potentials, and altogether we can sum them up to give a total hydraulic potential or total hydraulic head. And the strength of that hydraulic gradient, right, the difference in hydraulic head between 2 points, determines where the water flows and how fast. Right, so today we're just going to talk how can we quantitatively determine the effects of all those different forces acting on soil water, and can we actually measure the energy status of water in soil to work out which way it's flowing. And that's sort of today's lecture. Primarily we're going to be looking at water flow directions, and in upcoming lectures we'll talk about actual fluxes. So potential energy we define as the energy that has the capacity to do work. Might not necessarily be doing work, but it has the capacity to do that. It's sort of related to where things are in that field of energy. For example, where you are relative to, say, the surface of the Earth, or where you are relative to the Moon, for example. It may be due to a particular configuration. So, for example, it may be due to which soil pores are holding onto the water, which determine the matrix potential. So when we go back to our high school physics, energy is really force times a distance over which that force is being exerted. So, for example, we can measure the gravitational potential energy as being a gravitation force times some level h, height, right, some distance. And if you weighed 50 kilograms, you multiply yourself, that weight, by 9.81 meters per second squared, which is a gravitational acceleration, and that gives you your potential force. And if you were to fall from a certain height, that will give you, the potential energy that you have if you're a certain height. And the potential energy is the energy that you would gain by falling through that height. So we talk about potential energies, but also potential energy gradients. That's the differences in energy or potential energy between 2 points. So, I sort of interchangeably talk about potential and sometimes which has units of, it's the amount of work that's necessary that you move a unit volume of water from one point to another, right, on a volume basis. And potential head, on the other hand, is defined as the amount of work necessary to move a unit of water on a weight basis. And I'll give an example of what I mean by that in a sec. But both essentially refer to potential energy. So if you're a hydrogeologist, you might often talk about the groundwater head, which might vary from place to place. And if you stick a bore into the groundwater, measure the height of the water inside that bore, and that's the head that water has at that certain point, that certain amount of energy that it has. So if we look at soil water potential, we have energy divided by volume. Okay, so mass times gravity times height is our potential energy. Divide that by the volume. And for example, if we have that volume is over a certain area, A, multiply that by height, we get the volume. And so you can see that we end up having mass times gravity divided by area, and which is essentially a pressure unit, right? Force divided by area is pressure. In soil water potential head, on the other hand, we have energy divided by weight. So we have a length unit. We have our potential energy with mass times gravity times height, divided by our weight, which is mass times gravity, and we end up with just a length unit or head. But they're sort of both interrelated. So the pressure unit is related to the head unit, and it sort of depends on which mass we're referring to, which weight we're referring to, when we can relate the two. So for example, you might see matrix potential has units, and you would have seen it if you attended the computer labs and looked at the first tutorial. We had the matrix potential of some of those soil waters were in kilopascals, a pressure unit, but you had to convert between kilopascals and centimeters of water. And so by doing that conversion, you can do a conversion between pressure units, which is kilopascals, to centimeters of water, which is a length unit. So often we're interested in the total soil water potential at a point, because that's the thing that's going to determine where the water flows. So the total soil water potential is defined as the amount of work that must be done to move a tiny amount of water from one state, standard state, in the soil, in the liquid phase, by means of some externally applied force. It includes all the forces, so gravity, capillarity, which is the matrix potential, osmotic forces, which are differences in salt concentration, and pressure, etc. Okay. I'll give you some definitions of those in a sec. The primary components of the potential energy that impact water flow in soil, things like gravity, as I've already mentioned, so where the water is in the soil relative to some reference level. So if it's high up in the soil, it'll have more potential energy. If it's lower down in the soil, its potential energy will be smaller. Matrix potential, again, always negative when the soil is unsaturated. And you can only have matrix potential when you have an air-soil-water interface. So when you have saturated conditions, your matrix potential must be zero. On the other hand, if you're below the water table, then you'll have a hydrostatic pressure potential. And hydrostatic really means hydro, water, static is stationary, and it's really referring to the weight of water in saturated conditions above a certain point. Right? So if you're below the water table, it's really related to the pressure that's being exerted on you by the weight of that water. Imagine swimming down to the bottom of the swimming pool, and you feel the pressure on your ears. That's hydrostatic pressure potential pressing in. So the hydrostatic pressure potential, by definition, is always zero in the unsaturated zone, it's zero where you have air, water, and soil. And then finally, solute potential is sometimes important where we have big contrast in salinity or concentrations of things. And that does happen in soils. So we should sometimes consider that, particularly when you're thinking about plants and the salinity issues in the wheat belt. They can really impact water flow. So the osmotic potential is related to differences in concentration, which exert a force on water to try and balance those differences in concentration. So here's an example of the osmotic potential. Here we have a U-shaped tube with some sugar molecules on one side that have been dropped in, water initially in equilibrium on both sides of the tube, and then we have a semi-permeable membrane here, which is permeable to the water, but not permeable to the sugar molecules, so the sugar molecules can't flow through. So what happens is the water wants to balance out that concentration difference, so water flows through the permeable membrane, but the sugar molecules can't, and water flows through, but then it reaches a certain point where the weight of that water starts to press down against this concentration gradient, this osmotic potential, and then comes to some sort of equilibrium. And so the difference in the height of water we can measure as the osmotic potential that's given by the concentration of this solute. So it could be sugar, it could be salt, it could be some other sort of thing that has a concentration gradient. We have hydrostatic pressure potential, like I mentioned before. So this is a swimming pool analogy. This is the total height of saturated water above a point. So we use hydrostatic pressure potential in dams to generate hydropower, for example. And I've mentioned matrix potential before, right? So the soil water potential then is determined by the sum of all these different potentials. But we've got to remember that the absolute value of the potential energy can't be measured. All we can measure is differences between points or differences relative to some reference level. So potential energy differences are measurable, okay, unlike the absolute values. So we have the total potential energy, or total potential head, is the sum of all those potentials. So for example, the total potential head, H, is equal to the elevation potential or gravitational potential here, the matrix potential, H, and the pressure potential. And sometimes we use interchangeably these different types of terms. So we might use the psi term here with H, Z, M, and P representing each of these. Okay, so how do we use potentials? Well, we doing the calculations, we always define the coordinate system as being positive upwards. We choose an arbitrary reference level, for example, at which the gravitational potential is 0, and it doesn't matter where we choose that, as long as we choose one. And then we find a location where the water potential here is known. And I'll give you some examples which illustrate that. Then we discretize our space, divide up our space, and work out the total hydraulic potential at various points of interest. And calculate the differences between the two, between different places will tell us where the water's flowing. So here's the first example. Use of gravitational potential head in a soil. So here we have some sort of soil. We have 2 points in that soil, point A and point B, and we're going to arbitrarily choose some reference level. So relative to that reference level, A is 15 centimetres above it, B is 10 centimetres below it. So we look at the total potential energy difference between the 2 points. We have the potential energy of point A, gravitational potential that is, of 15 centimetres. The gravitational potential of point B is negative 10 centimetres because it's our coordinate system is positive upwards. And so when we sum those potentials, we have where we work out the difference in potential energy, 15 centimetres. Take away negative 10 centimetres, which is really a positive, so we have 15 plus 10, which is 25 centimetres. Here's the same example, except we've just shifted the reference level. So we've got point A and B again. Our reference level now is up here. So relative to that reference level, the gravitational potential energy of point A is 5 centimetres. The gravitational potential energy of B now is negative 20 centimetres. We do the sum and we end up with the potential energy difference is exactly the same, 25 centimetres. Okay. So that's a little bit trivial, but now we can actually use it to estimate various things about where water is in soil. So here we have depth on this axis, and on this axis is the potential energy, potential head. And we're given the question. So the soil in which the liquid water is in equilibrium with the water table. So when you have a question that says things are in equilibrium, it means things are not moving or changing with time. Okay? So we have a water table at minus 70 centimetres down here. And the reference level is chosen as being minus 70 centimetres. Okay. So we can immediately calculate our elevation potential or gravitational potential, which is psi z. So we go in here and it's 0 here because we're at the reference level. And if we move up to this point, we're 10 centimetres above that reference level. Now we're 20 centimetres, 30, and then 70 centimetres above that reference level. Okay? below the reference level, then our gravitational potential decreases. Okay. There's another clue as well, right? So we're told that the water table's at minus 70 centimetres. So if we look at our pressure potential, that means above minus 70 centimetres depth, right? We're in the unsaturated zone up here, so that means our pressure potentials must be 0. And as we go 10 centimetres below the water table, then our pressure potential increases to 10 centimetres. As we go to 20 centimetres below the water table, then our pressure potential increases to 20 centimetres, and so on, until we're down to 40 centimetres at this depth. So now we have the gravitational potential and the pressure potential. So we can also calculate now the soil matrix potential, because we're told one other thing, right? We're told that the water is in equilibrium with the water table, so it's not moving. So let's go back to the water table, because we know that the matrix potential at the water table should be 0 as well. Okay? There's just a tiny amount of saturated conditions at the water table, so there can't be any matrix potential. So if we sum up the pressure potential, the matrix potential, and the elevation potential, then we get the total hydraulic head is the sum of those three. 0 plus 0 plus 0 is 0. That means if water's not flowing, then there should be no difference in total hydraulic head between any of these 2 points. So that means the pressure potentials at all these other points, the total hydraulic head at all these other points should also be 0. So now we can go back and calculate our matrix potentials. And we know that below the water table, they must be 0. So let's double check what our total hydraulic head is below the water table. We have 10 centimetres, take away 10 centimetres is 0. Right? 20, take 20 is 0. 30, take 30 is 0. And 40, take 40 is 0. Right? So below the water table, there's no water flow. Now we go above the water table, and we know there that the total hydraulic head is 0 centimetres. Then if we have an elevation potential here of 10, a pressure potential of 0, then the matrix potential must be minus 10 centimetres. And same at this point here. We have a gravitational potential of 20 centimetres. Our pressure potential is 0, but the total hydraulic head is 0, so that means the matrix potential must be minus 20 centimetres. So as we move up above the water table, our matrix potential is becoming more and more negative, which means we're getting more and more unsaturated conditions in the soil. Soil has more and more air in it closer to the surface. Okay. So if we knew our water retention function, we could put these numbers into our water retention function and calculate the water content from our water retention function. Right, so I've got some examples here, and I'm going to give the answers to these in the next lecture. But I'd like you guys to try and work through this question based on what I've just said. So this question here is exactly the same as the previous question, right? It says the conditions for example 2.7, which is on the previous slide. Except the only difference is they've moved the reference level now from the water table, which was down here, up to the soil surface. These depth increments are all the same. And actually, I should move that slide to the side. So let me do that. 2, 6. Okay. There we go. So this question is exactly the same as the previous question, except for one difference. We've moved the reference level from here, which was at minus 70 centimetres. Now the reference level to calculate the elevation potential is now at the soil surface. Again, we have hydrostatic conditions, so we have no water flow happening. Right? There's no difference in total hydraulic head between the 2 points. But what I want you to do is go and calculate the pressure potential, the matrix potential, the elevation potential, and the total hydraulic potential, given that we've shifted this point up to here, and then tell me what you see. So this is just reiterating some of this, right? And I can show you here an example where actually water flows uphill, because water doesn't necessarily have to flow downhill always. It always has to flow down an energy gradient. So when we have a difference in energy that's big enough, water can actually flow uphill. So here's an example. Here we have point A in the soil and point B in the soil again, some reference level. And over in the table here, you can see the actual numbers. So we said the point A is 10 centimetres above that reference level. Point B is 12 centimetres below that reference level. They've used an instrument to measure the matrix potential in the soil, a tensiometer probably, and at point A, the tensiometer is reading minus 50 centimetres. At point B, the tensiometer reads minus 25 centimetres of matrix potential. It's unsaturated conditions, so our pressure potentials are both zero. Now, if we sum all our potentials up, we get the total hydraulic head. And the total hydraulic head is the sum of these three. So 10 minus 50 plus 0 is minus 40. And at point B, negative 12, take 25, plus 0 is minus 37 centimetres. And you'll see that the difference in hydraulic head, minus 40 minus minus 37, is actually minus 3. And because this one's lower, water always flows from high to low total hydraulic head. So water wants to flow in this soil uphill from B to A. Now, we often use what's called the hydraulic gradient in soil. So it's the relative difference in hydraulic heads, or the difference in hydraulic heads between 2 points, divided by the distance between those 2 points, which determines what's called the hydraulic gradient. Right? It's like the slope of the total hydraulic head with distance. So in this case, we've got the total hydraulic head at A is negative 10 hectopascals in terms of pressure. The total hydraulic head at B is minus 20 hectopascals. And let's say there's a 10 centimetre difference between the two, between A and B. What do you think the hydraulic gradient is? Okay, skip that. There's an example. This example here used 15 centimetres difference between the 2 points. And I'll let you guys work through that. Okay, so just things to maybe help you remember. If we recall that the coordinate system is positive upwards, right? If the hydraulic gradient is negative, right? Then we have upward flow. Right? The hydraulic gradient is 0, we have no flow. If the difference in the hydraulic gradient is 0, we have no flow. The hydraulic gradient is positive, we have downward flow. So that's the water flux. However, if the hydraulic gradient is upwards, the water flux is defined as being positive, because we define our coordinate system as being positive upwards. If the hydraulic gradient is 0, the water flux is 0, right? Doesn't flow in any direction. If the hydraulic gradient is downward, if our hydraulic gradient is positive, the water flows downwards, and the water flux is defined as being negative, because we've defined positive as being up. Just ignore that. Remember this for Thursday's lab. That was last year's slide. So I've provided another example here, and maybe you guys can work through this to determine. I may have already given the answers in some of this in the lecture slides, but it might be worth your while to work through this and see if you can do the calculations yourself, so you're confident in being able to do it. In this case, we have a slightly different question. This time water is flowing through the soil, so there will be differences in the total hydraulic head between points. Right? A soil in which water is flowing into a drain at minus 40 centimetres. So there's a clue. At minus 40 centimetres, our water table, that we must have a water table here. Otherwise, water wouldn't be flowing into a drain. Okay. The reference level for our gravitational potential energy calculations is at 0 at the soil surface. And we have made estimates of the matrix potential from previous measurements. Right? These are estimated. So your job is to calculate the elevation potential, the pressure potential, and the matrix potential, and the total hydraulic head in this soil, and work out where water is flowing, whether it's upwards or downwards. Right? Work out your hydraulic gradient between 2 points. Here's another example. Water is evaporating at the soil surface. There's a water table at minus 40 centimetres. The reference level is again at the soil surface. Matrix potential has been estimated by measurements in the soil. So the answer is given down here, but see if you can work out the pressure potential, the elevation potential, the total hydraulic head, and see if you can calculate the hydraulic gradient between 2 points, and then estimate the directions of water flow. Last example. Again, you can do these calculations. The soil is initially quite dry. It received rain that wet the soil from the surface partway through the profile. After a few days, the soil dries at the surface, probably, and water moves upwards in response to evaporation. But further down the profile, at lower depths, water is still moving down from that previous rainfall event. Matrix potential has been measured. Assume a reference level somewhere. Calculate your elevation potential, your pressure potential, and your total hydraulic head. Bearing in mind that you've got to work out under what conditions this is not 0, or if it's ever not 0. Okay? Let me go through, was that everything? That's the end of the lecture. If you can't find the answers in the lecture notes, I'm sure they're there, come to the lecture anyway and ask questions about how to do these calculations to understand how to use measurements like this to work out which directions water is flowing in soil. Okay.